We're now in section 3.4. We're making a lot of progress. Chapter 3 is going to close out with section 3.4 and 3.5, and both sections talk about eigenvalues and eigenvectors. Here we're going to introduce the idea, and in the next section, the last section of chapter 3, we're going to talk about some cool applications of eigenvalues and eigenvectors, one of which is the PageRank algorithm that Google uses, which is super valuable. In fact, there was a chapter of a book that was written recently called the $25 billion Eigenvector, and it's born of the ideas that we're going to be talking about today. Okay, before we can really dive into a $25 billion eigenvector or know how to construct one, let's start at the beginning of what these things even are. So let's say that we're in R2 and we have the matrix 5, 4, 1, 2. So we've already learned that this matrix represents a linear transformation. It will take some vectors and move them around, just through multiplication. Multiplying this matrix by a vector is a transformation. It's like a function in R2. It takes a vector and you give it an input, and this matrix will give you some output. So let's see where this matrix takes the vector. We could take really any vector. How about 1, 2? So here is the vector 1, 2, 1, 1, 2. It's right up here. And we're going to see where it goes under this transformation. Okay, 5 times 1 is 5, plus 8 is 13. Actually, let's write it like this. So 13, and 1 times 1 is 1, 13, 5. Okay, so that original matrix 1, 2 goes to 13, 5. And this is a pretty typical thing that will happen. We have this transformation, we multiply it by the vector. This is sort of transforming this vector into a new vector. So here's the old vector, and this matrix, which represents a linear transformation, transformed the vector into this one. Now let's see where another vector goes under this transformation, and let's look at the vector -1, 1. So we do this transformation, which is just the matrix multiplication, and we'll get, let's see here, -5 plus 4 is -1. And then 1 times -1, -1 plus 2 is 1. So this is something interesting. This matrix -1, 1, which is right here. Let's see, -1, 1. It's a little short vector guy right here. And it goes through the transformation, and when it does go through the transformation, it actually lands on itself. So after going through the transformation, this vector right here just stayed put. So this is an interesting case. This vector stayed put, stayed where it was. The input equaled the output through the transformation. Let's try one more just so we can see what else there is to see. Okay, we'll look at one more, and this time we're going to once again take this matrix, which is a linear transformation, multiply it by some vector, and see where that vector ends up. And the vector that I want to look at this time is the vector 4, 1. So where does 4, 1 go under this transformation? So this will be 24, and then 4 times 2, and then plus 2 is 6. Okay, so we get the vector 24, 6, which is, let's see, the original vector was 4, 1, so it was right kind of in here. And then we get a new vector 24, 6, which is way off here somewhere, through there. Okay, I want to draw this slightly more accurately. 24, 6 should be probably somewhere in here. And it actually, and you can probably tell this from the the vector itself, this guy right here, when we took this vector through the transformation, we landed on something that was a multiple of the original vector that was being transformed. So this is a different case. That never happened with the first one. The first one we just got two totally random vectors, but this case right here we landed on the same thing, and this case right here we landed on a multiple of the original input vector. You can say, okay, this is actually a multiple of the input vector in that transformation. And so these are two kind of special cases, this one right here, and very similar, this case right here, where these kind of special vectors here are going through the transformation, but they're kind of staying put, or at least they're staying on the span of the original vector. And these are the special types of vectors that we're talking about here today. And these are actually going to turn out to be eigenvectors. The type of vector that you put it through a transformation and it sort of stays on its own span. It's either just stays exactly where it was, or it becomes some multiple of where it was, some scalar multiple of the original vector. These are eigenvectors. And interestingly, this vector and this vector, they won't be eigenvectors for other matrices. They are linked with this matrix. They're eigenvectors of this matrix right here. Another random 2 by 2 matrix may throw these completely into different places. But for this matrix here, it sort of keeps it close to where it was originally. So this is an eigenvector of the matrix 5, 4, 1, 2. This is an eigenvector of the matrix 5, 4, 1, 2. And this guy here is not an eigenvector of the matrix 5, 4, 1, 2. And it's much more common to not be an eigenvector to actually be an eigenvector than to be one. You know, these are actually the only two eigenvectors for this matrix out of all the possible vectors in R2. These are the only ones that behave like this. There's only these two. And several more vectors just get thrown, you know, randomly around by that transformation. So this was just kind of introducing us to the idea of eigenvectors, and I haven't even told you yet what eigenvalues are, but I will tell you that the eigenvalue of this eigenvector is 1, and the eigenvalue of this eigenvector is 6, and you can probably figure out where eigenvalues come from. But this is just an introduction. So there's two things that we want to remember as we delve into eigenvectors. And the first thing is we always want to be thinking of matrices as linear transformations. So a matrix is a linear transformation. In here, it was in R2, it was really easy to visualize, but it really is a linear transformation, whatever dimension you're talking about. You could be in R7, R8. You're going to be taking a vector and transforming it or moving it to very possibly another vector in your vector space. And the other thing to remember is the word span and what that means. So what is the span of some random vector? Say that we have a vector v here, and what is the span of the vector v? Well, it's any, you know, scalar multiple of that vector. So it could be any vector along this line or even this line if we used a negative scalar. So this line represents the span of v. And what we saw up here was this eigenvector, once it went through the transformation, it didn't land back on itself, but it landed somewhere on its span. It landed at 24, 6, which is a point on its span. And so that was okay. So what is the span of a vector? It's all scalar multiples of that vector. And we could be in 2 dimensions, 3 dimensions, however many you want, but it's just a scalar multiple of the vector. Okay, so a scalar multiple of the vector. These two ideas we want to keep in the front of our brains as we keep talking about eigenvectors. Now that we sort of know what they are, we want to know how to find them. And actually, before we even talk about how to find them. Why do we use this term eigen? In German, the translation is own. So your own vector, your own. So it's like your own self, if you're a vector, or one that's really related to it. And so what we're going to be looking for when we look for these eigenvectors is we want a vector that we have this matrix A, which is a linear transformation, and say that we have some vector x. So this is an n by 1 vector. And once x goes through the transformation of this being multiplied by this matrix, we want it to land on itself, or we want it to land as a multiple of itself. So we want that ax to equal either x or some multiple, and it's the convention to use the Greek letter lambda as a constant. So this guy right here, let's see, this guy right here is a matrix, and we know that this guy right here is a vector, and same guy right there. This is a constant. And so this right here is actually the eigenvector. If this relationship holds, this is the eigenvector, and this constant is the eigenvalue. What did you have to multiply it, the vector by to make this statement true? So this is the really important relationship that we have a matrix. It gets multiplied by this eigenvector, and when that happens, and it usually doesn't happen this way, but when you have an eigenvector, it lands through the transformation on some multiple of itself. So this is a very special relationship, and now knowing this relationship, we'll talk about how to find the eigenvectors and eigenvalues. Up here, I just told you what they were, but one of your biggest jobs in this section is to be able to find these guys. So this is the job we want to be able to do, sort of our quest, a skill that we definitely want to develop. Given a matrix A, we want to be able to find its eigenvalues and eigenvectors. And this is the order that we do find them in. We first find the eigenvalues, and then those lead us to the eigenvectors. And so this set of vectors for a matrix is very special. It's a special small set of all the vectors that the matrix, you can run through this transformation. This little tiny set of vectors are the only ones that stay on their span through the transformation. And so that's a very special set to this particular matrix. So we know our important formula is this AX equals lambda x, where x is a vector, A is a matrix, and lambda is a constant or a scalar. So I said that the first thing we were going to do was find eigenvalues. So this will be our first job, is to find the eigenvalue, and then after we do that, we'll go back and find the eigenvectors. And so remember, in this relationship, this special relationship, the only thing that we're given is a matrix A. We're trying to find all the vectors that satisfy this relationship for A. So basically with eigenvectors, eigenvalues, you're just thrown some random square matrix A, and the job is to find these other parts. And these other parts are very special. They're the only vectors that stay on their span when they go through the transformation of the vector A. And like we talked before, there's relatively few of them. So what we're going to do is run through a few logical steps that will lead to a certain method to finding these eigenvalues. So first of all, the very first thing that I notice is if that first statement's true, then this statement is true. I can subtract that from the so this guy right here is lambda times a vector. So this is a vector, and this is actually a vector too, an n by 1 vector. And so this will just be some other n by 1 vector, and this guy right here is actually the 0 vector. Okay, but everything's legal, all of that is fine to do. So if this is true, then we can definitely say that this is true. Now I want to go over here for a minute and explore one thing. So here's our x vector. We don't know what it is yet. But lambda times x, which is just this right here, will be lambda x1, lambda x2, all the way down to lambda xn. Okay, what about this matrix, this n by n matrix? It's the identity matrix multiplied by lambda. So we have lambdas all the way on the diagonal, and then zeros above and below that. What if I took that and multiplied it by the x vector? Think about what you would get if you did this multiplication. Okay, so we would get, let's see, this top row by the vector, that would pick up x1, so that would be lambda x1. And then this second row by the vector, we'd get zeros everywhere except lambda times x2, so this would be lambda x2. And then we can keep doing that, picking up x3, lambda x3, all the way to the last one where we would have all zeros and then a lambda times xn. Lambda xn. It turns out that these are actually equal. You know, you can take lambda times the x vector, or you can take lambda times the identity matrix times the x vector, and you get the same result. So I'm going to substitute that in here because I really want the ability to in my next step, you'll see something I want to do. I want to be able to sort of factor this a out, but I can't do it because a and lambda are totally different objects. This is a scalar, this is a matrix, so I can't treat them the same. But knowing this, what I've just shown is that lambda x, so lambda times the x vector, is actually the same thing as lambda times the identity matrix of size n times the x vector. And so I'm going to use this fact right here. And I know that just because I worked it out up here. So over here, we're still working on a logical sequence of steps. If this is true, then I'm going to substitute this lambda x for lambda times the identity matrix times x. All this work here was done to show that this is the same thing. So we're going to say, if this is true, then I can say the matrix A times our vector x minus lambda times the identity matrix times the vector x is that zero vector. Okay, why the heck did I do that? Who cares? You know, why did I go through that trouble? This is an n by n matrix. This also is an n by n matrix. And so that is something, those two things can be added or subtracted together. If it wasn't the same size, we wouldn't be able to add or subtract them together. But what I want to be able to do now is say, okay, wouldn't this be true also then? Okay, so all I've done is I've factored this x vector out. And think about multiplying this back through with the distributive property. This would be a times x, okay, minus lambda in times x, okay, equals 0. That's definitely the same thing. I had to use this instead of just lambda because it would make no sense. A statement like this makes no sense. You can't have a matrix minus a scalar. That they don't go together that way. So I had to construct another matrix that did the same job as this scalar up here. And then this matrix is totally fine. This is an n by n matrix, and you can subtract it from A. So that's what all of this work here was done. Okay, so now I know that this is true. And I'm just going to move this guy over. He was kind of a minor part of the proof that we're doing, but we don't want to get him mixed up with the real important parts of this whole logic statement. Okay, this right here is an n by n matrix. This right here is a vector, an n by 1 vector, and this right here is an n by 1 vector. And remember, in all of this, we're trying to find the eigenvectors. So we're really trying to find that x and the eigenvalues here. Now think about this equation here. This equation will work. We can find a solution for x without even thinking too hard about it. What if x was the zero vector? A matrix times the zero vector definitely equals the zero vector. So it will work when x is the zero vector. But that's not terribly interesting and usually not very helpful. So we ask, when else does it work? So one solution is, or would be, that this equals, 0, 0, or equals the zero vector. But are there other solutions? Are there other x's, x vectors, that would make this whole statement true? And that's what we're on the hunt for. That's what we want to find. So this really is a matrix equation. And remember, matrix systems of linear equations, which this is a matrix equation, they either have no solutions, one solution, or many solutions. We know that there's one solution. So we're asking, could there be more? And if there's more, then there's many solutions. And we can think of this as really some matrix B, which is just all of this. If we put it, we could just call all of this some matrix B times the vector x equals 0. Are there more solutions? At this point, I want us to go back to the last section because we're going to sort of invoke this theorem right here. This was a very important theorem that we talked about. If we have a matrix equation, how do we get many solutions? What does that have to do with the determinant? We're kind of looking at this point for many solutions because what we were doing just a minute ago, this guy right here, which we've just simplified to this, we're looking for more solutions. We want more solutions. And so we go back to what we developed last time, and if there are going to be many solutions, whoa, that coefficient matrix determinant has to equal 0. Okay, so this is the fact, this is why eigenvalues and eigenvectors are in this chapter, because we're going to rely on this fact. If there truly are more solutions to that matrix equation, then the determinant has to equal 0. So that's what we're going to use. Okay, so all along we're going to remember that if we truly want more than one solution, which the only option is to have many solutions, then we have to have the determinant of the coefficient matrix, which in this case is B, to equal 0. So we really need for the determinant of B to equal 0. Well, B is just this guy right here. I just wrote B because it was a little simpler than I wanted us to really remember that this is just a matrix, this big long expression here. So I'm going to stop talking about B and go back to my A minus lambda in. This is the guy that I really want the determinant to equal 0. If it does, if we can find this happening, then we have a good shot of finding many solutions, many places where this is true, which goes back through a logical sequence of steps, and we can find those vectors where this is true. And this is the relationship that we really care about here, this eigenvalue eigenvector relationship. So if we can find where this is true, then we can find where this is true. And so this becomes really our job. So this is now our quest, and we're going to first find the lambdas that make this true, and then we'll find, back here, once we know what the lambdas are, we can go back and find those eigenvectors. So find the eigenvectors that make that true also. Or let me say it like this, that flow from knowing what those eigenvalues are. So this is it. This is going to be our method here for finding eigenvectors and eigenvalues. And if someone just threw this at you, just knowing this, you would say, where the heck did that come from? But it really does come from a sequence of logical steps that leads us to this. So this is now our method, the method to finding eigenvalues and eigenvectors. there. So we've just spent a lot of time on theory. Now let's head towards a real practical example, and we'll find some actual eigenvectors and eigenvalues. So here we have this 2 by 2 matrix, and we're asked to find A's eigenvalues and eigenvectors. And we've actually seen this guy before. He was the very first example of this section. So we know that our method is going to be find all the lambdas that make this statement true. The determinant of A minus lambda I has to equal 0. So let's see, let's figure out what this would even look like here. So A minus lambda I would be 5, 4, 1, 2 minus lambda times the identity matrix, which equals 5, 4, 1, 2 minus, I'm going to multiply that lambda through, that'll be lambda times 0 is just 0, lambda times 0 is 0, like that. And I can put this in one matrix. So this is 5 minus lambda, 4 minus 0 is 4, 1 minus 0 is 1, and then 2 minus lambda. Okay, that's the matrix, and I need its determinant. So we need the determinant, 5 minus lambda, 4, 1, 2 minus lambda, to equal 0. Luckily, this is a 2 by 2 case, and finding the determinant isn't too awful, but we're going to... So to find the determinant of this guy, I just need to take this times this minus this product here. And that's going to be 5 minus lambda times 2 minus lambda minus 4 times 1 equals 0. And I'll multiply this out. That's 10 minus 5 lambda minus 2 lambda is minus 7 lambda plus lambda squared minus 4 equals 0. I just keep working. This is a quadratic equation. So lambda squared minus 7 lambda looks like plus 6 equals 0. And that I can actually factor. It's lambda minus 6, lambda minus 1 equals 0. So this is awesome. I found two lambdas. Lambda equals 6 and 1. So these are my eigenvalues here. Okay, so that's awesome. I found my eigenvalues. Let's just remember what we did. We knew that we needed to find this A minus lambda I. This work was just finding a single matrix that represented that. And then we knew that the determinant of that had to equal 0 if we were going to find multiple places that the eigenvector equation held true. And doing this, it just led us to this polynomial to solve. That was not too bad, and we did that, and we found out that when lambda equals 6 or 1, this determinant will be 0, and that's the only time it happens. Okay, so remember, once we find the eigenvalues, we go back and find the eigenvectors. This was our plan all along. The method was we want to solve this equation, but it's equivalent to solving this equation here. And so we needed to find the lambdas where that is true, and then find the vectors, the eigenvectors that flow from that being true. So let's go back here, and we know what our eigenvalues are. So we're going to split this into two cases. What happens if lambda equals 6, and what happens if lambda equals 1? So if lambda equals 6, then I have, just looking right here, I've got the vector 5 minus 6, 4, 1, 2 minus 6, which is the matrix. I don't know if I said vector before, but I mean the matrix. Negative 1, 4, 1, negative 4. Okay, and so we always have to keep reminding ourselves, now what is it that I want? But really we want this relationship. We want to find the x where this is true, and in this case, where does ax equals 6x. So in a similar way that we can say ax minus 6I times x equals 0. So a minus 6 times the identity matrix times this vector x that we're looking for equals 0. And this right here is a minus 6i. I went through that work already to do it. So this is our a minus 6i matrix. And so we want to know, when does negative 1, 4, 1, negative 4 equal times our eigenvector, x1, x2. When does this equal 0? And I'm going to move this guy over because I'm going to need more space, I just realized. Okay, so I'm also going to, call this, the 0 vector is 0, 0. This is stuff we were doing the first few weeks of class to solve an equation like this. And so we would put this in reduced row echelon form, the augmented matrix. So let's take this and go up here and solve this system of equations. And it definitely looks suspicious. We're going to put it through reduced row echelon form. And what we get out is the matrix 1, negative 4, 0, and then a bunch of zeros. And we're going to read off the solutions from this. So reading the solutions off of this matrix, we know that x1 minus 4x2 equals 0. So if we say, so x1 minus 4x2 equals 0, let x2 equal r, then x1 is 4r. And so the solutions are 4, 1, and then any multiple of that vector. And this is the eigenvector here. And any multiple would work for this equation here. So this is the eigenvector for the eigenvalue lambda equals 6. There's actually another eigenvector for the eigenvalue lambda equals 1, which we'll find in a minute, but we've found this guy. We're going to continue the example, and now we want to find the eigenvector for the eigenvalue lambda equals 1. So what are the vectors x such that ax equals 1, that eigenvalue times the vector x? And same story as before, 1 times the identity matrix x, and so we can subtract that. We don't really need that 1 anymore. But this will all equal 0, a minus I times x equals 0. And a minus I, let's see, the matrix A was 5, 4, 1, 2. So 5, 4, 1, 2 minus the identity matrix. And that times x will equal this guy. So the matrix is 4, 4, 1, 1, and x1, x2 equals 0. Again, this is a matrix equation that we could have solved pretty much the first week of class. And even looking at it, we can probably solve it without putting it through reduced row echelon form. But when we do put it through reduced row echelon form, we get this. So this says that x1 plus x2 equals 0, which just means that x1 and x2, so x1 equals negative x2, and so the solutions look like something like this. These are the solutions. And so this is the eigenvector for when lambda equals 1, for that eigenvalue. So the matrix A equals 5, 4, 2, 1 has two eigenvectors. Well, it has two eigenvalues, which are lambda equals 1 and 6, and the corresponding eigenvectors. You can't have an eigenvalue without an eigenvector. They go together. For the eigenvalue lambda equals 1, it was negative 1, 1. And for 6, it was 4, 1. So what we've done is we have just found the eigenvalues and eigenvectors for this matrix. And that's the job that you're going to have in this section, is they're going to give you a matrix and say find its eigenvalues and eigenvectors. So we did all that work to find this solution. As you practice, you'll get way quicker. We've kind of gone through the logic of everything each time, but really you're focused on finding where this determinant equals 0, and then plug those lambdas back into, this equation, right up here, and then you'll find your solutions pretty quickly. Let's try a 3 by 3 case. Okay, this time we're going to find the eigenvalues and eigenvectors of a larger matrix and see if it gets any trickier. And the matrix that we're going to work with is A equals 5, 4, 2, 4, 5, 2, and then 2, 2, 2. So like before, I really care about this quantity here, the determinant of A minus lambda I. I'm looking for those lambdas where this equals 0. And so the determinant of this will be, let's see, I'm going to just subtract off my lambdas. Everywhere else stays the same. 2, 2, 2 minus lambda. So where does this determinant equal 0? And already I can see that this is going to be way tougher than the 2 by 2 case because finding the determinant of a 3 by 3 matrix just is inherently more difficult. But I can make it easier by simplifying this determinant. Remember, some of those elementary row operations don't change the determinant or change it very little. So let's use that to our advantage. One thing I'm going to do is I'm going to try to get rid of this 2 right here, and I can do it by adding a -1 times this row to this row up here, and I'll create a 0. I love zeros when I'm finding a determinant because it makes everything simpler. So I'm going to take negative row 2 and add it to row 1. This is adding a multiple of one row to another, and so the determinants are equal. It won't change. So first of all, my bottom row stays the same, and actually the second row stays the same. It's just the top row that changes. Okay, so I've got to think through what's going on. -4 plus this, and that'll be -4 plus 5 minus lambda will be 1 minus lambda. Then 5 minus lambda times -1 is a -5 plus lambda plus 4. So -5 plus 4 is -1, and then plus lambda will be -1 plus lambda. And then what I really wanted was the -2 plus 2 becomes a 0. Okay? And then I just noticed that these are actually opposites of each other. So what I could do is say column 1 plus column 2 as my row operation. That won't change the determinant either. So this is going to be column 1 plus column 2, which means only column 2 changes. So 1 minus lambda, 4, 2, 0, 2, 2 minus lambda. Okay, so we're going to add these together. This plus this equals 0. And this plus this is 9 minus lambda. And this plus this is 4. And now I'll go ahead and find my determinant from there. I've got a lot of good zeros. I'll just do cofactor expansion along the top row. So I'm going to do my cofactor expansion, and I'm going to use this guy. So blocking out this and this is 1 minus lambda times the determinant of what's left. And that will be 9 minus lambda times 2 minus lambda minus 8, it looks like. And I really want this determinant to equal 0. That's the first time I've said that, but we know we want this to equal 0. From here, solving these equations can get a little bit tricky. Usually in the examples, they'll give you things that kind of work out factor-wise. I know I'm going to have some type of cubic equation here. I'm going to hope for this inside being able to factor on its own. So let's just try that first of all. 1 minus lambda. This is going to be 18 minus 11 lambda plus lambda squared minus 8 equals 0. 1 minus lambda still hanging out. And then I've got lambda squared minus 11 lambda plus 10. That looks very hopeful because I'm pretty sure I can factor that. Lambda minus 10, lambda minus 1 equals 0. So I know that lambda equals 1 or 10. And the 1 shows up twice, but I just have to list it once. These are my eigenvalues. What if you'd gone through this 3 by 3 case and it was just like a bear to factor, like it was not possible to just look at it and factor like I have done here? Well, you would have a cubic equation, and you could do something like graph it on Desmos, and you could find where it all equaled 0, just find the x-intercept. So Desmos could solve this for you graphically pretty quickly also. But this one was nice, it factored out. If it doesn't, just use Desmos, graph the cubic function, and see where it equals 0. But I have my eigenvalues, now I'm going to go back and find my eigenvectors. So we're going to find our eigenvectors, and we're going to start with the eigenvalue lambda equals 10. So that means I have to find all the x where this equation is true, a minus 10i x equals 0. So here's my x, here's my x, here's my 0 vector, here's my 0 vector. Now I just have to write out what a minus 10i is. And this is essentially going to be the matrix A with just some of the diagonal elements. These guys each need to have 10 subtracted from them. So only the diagonal elements change. 5 minus 10 is negative 5. 5 minus 10 is negative 5. And then 2 minus 10 is negative 8. This is the equation I am going to solve, and it's going to pop out the eigenvectors. So I went ahead and put my system into an augmented matrix. I put it through a reduced row echelon form just on my calculator, and this is what I get out. And I can read the solutions off of this. We can tell this is a dependent system, but we totally expected that. That's the whole reason we've gone through this process, and it's pretty easy to read off the solutions from this. So this up here tells us that x1 equals 2 times x3. This right here tells us that x2 equals 2 times x3. So our solutions will look something like this: 2, 2, 1. And if we want all the solutions, we add this scalar r, because it'll work for any of these. But this is our eigenvector that corresponds to this eigenvalue here. So it's our eigenvector for lambda equals 10, and our only job is now to go find the eigenvector that corresponds to lambda equals 1. So this time it's our matrix A minus 1, because this was our eigenvalue, times the identity matrix of size 3 times the x vector will equal 0. And we're remembering that this is our original matrix A, so we can find this pretty easily. So this is the new part of the matrix. I just had to subtract 1 from each of these diagonal elements, otherwise everything's the same, and it's the augmented matrix. We're going to put it through reduced row echelon form and see what comes out of that. So we get this out of the reduced row echelon form, and I'm beginning to suspect something. I think we're going to get 2 vectors out of this as solutions. So the top row, which is all we have to go off, tells us this relationship between the 3 variables. And if we let x3 equal r and x2 equal s, then x1 will equal negative s minus 1/2 r. And so we get a solution that looks like this: negative s minus 1/2 r s r, which is written as negative 1, 1, 0 plus r times negative 1/2, 0, 1. So what we're getting here are these eigenvectors here, and we're actually getting an eigenspace. I mean, we were getting that before because this is a vector space here, but this has to do with the fact that this has multiplicity too, this lambda equals 1. Remember, it actually showed up twice in this characteristic polynomial here. And so we're going to get both of these as eigenvectors. Okay, so we've done it. We've found these eigenvectors for lambda equals 1, and we have our eigenvector for lambda equals 10. Whew, man, that was a long process. Okay, so thank heavens we can celebrate. We're done with that whole long process. It is a long process, but remember, knowing things like this leads you to the $25 billion prize at Google. Okay, it's probably a little bit more involved than what we've done here, but these are the beginnings of big ideas, and these are awesome ideas that have serious ramifications and serious benefits, and really are helpful in a lot of applications. That's what we're going to examine more of in the next section.